Okay, so today, our topic is hierarchical analysis of variance. This is a kind of analysis, a kind of design that I implore you to never use. Please. It's evil. But it's something I think you should know about, because it might be something you run into. Usually all of our factors are independent variables. So you'll hear me call them factors a lot. It's just another term. It's like how error and residual mean the same thing. Are crossed with each other. In other words, all the levels of A occur with all the levels of B. Things like that. Okay? In fact, it's probably hard for you to conceive of a design where that wouldn't be the case. And I'm not talking about subjects here. They're often nested, right? We just did a quiz, and it had the example of, subjects that are within A, B, or subjects within B, or within A, or whatever. So we often have subjects that are nested. What about nesting factors? So that's what I'm going to talk about today. In this, I know you can see those of you who looked at the notes in advance, and you say, there's 6 pages of, yeah, it's because this is a weird thing, and I want you to get it, so please feel free to, as usual, ask questions. So sometimes things are a little bit weird. I've never seen a design like this done on purpose. If I say that, you say, right? See, people do these things by mistake because they screw up their design. There's an old buddy of mine in undergrad who's here behind me, a guy named John, and what John did is he his honors thesis experiment, and then he went to analyze it, and I was in grad school by then, and he was in 4th year, and he sent me an email, and I replied, dude, you have nested factors, and he replied, I don't know what that means. And I replied, did you take 3 and 1? Anyway. So this is an actual design from an actual study. An acquaintance of mine back in grad school did some consulting. And one of the things you can do if you do go to graduate school and you're in something like psychology or biology where you do a lot of statistics, one of the cool things that you can do, in fact, is pick up extra money by being a statistical consultant. Because people don't know how to do it. And people are willing to pay people. I don't mean at universities, because obviously at a university, there are departments that deal with these things. But if you are just some guy doing a study, or some consortium of hospitals in Toronto doing a study on different drugs, maybe you have to hire someone, and you can charge them $250 an hour because they know how to do it. And so that's my friend. Yes.
Yeah. So maybe I should just wait.
Okay.
You're about to explain everything.
Okay. We have 3 hospitals. Like I said, this is a real design. This actually happened. And we have 6 drugs. And these are pain reduction drugs for people that have that were burn survivors, severe burn survivors, people getting skin grafts out of it. So there were 5 burn survivors in each group, 1 to 6. There are 3 hospitals, and there are 6 drugs. You probably want to put hospital in the model just because different hospitals have different staffs. They might have somewhat different ways they run things. The food's different at different hospitals. All garbage, but it's still different in each place. So it's going to be somewhat different in each place. So we have to consider hospital as a variable because maybe some of the groups report less pain because of the way they're being treated, not because of the treatment. Because the treatment we're interested in is the drugs. And as I said, this actually was a real study that was done. And because you might think, well, why wouldn't you just do a 3 by 6, right? So 3 hospitals, 6 groups. Because happily, there weren't enough burn survivors, like there weren't enough people with severe burns to do a study like this, where you have all levels of drug and all levels of hospital crossed with each other. So in this case, what you have is you have drugs are nested within hospitals. So drugs 1 and 2 are in hospital 1, drugs 3 and 4 are in hospital 2, and drugs 5 and 6 are in hospital 3. But no, for example, there's no hospital 3 and drug 2. That cell does not exist in this design. Ideally, that's what you would want. But like I said, it's a happy problem if there weren't enough people that were severely burned to be participants in this study. So things, like I said, it's a bit different than what we're used to because we have hospitals as a factor. And then we have 3 degrees of freedom there. Or sorry, 2 degrees of freedom, 3 hospitals. And we have drugs within hospital, which has D-1, which is, you're going to say, wait, Dave, there's 6 drugs. Yeah, but within each hospital, there are 2 drugs. So 2 minus 1 is 1 times 3, so it has 3 degrees of freedom. And it's subjects within drugs by hospital. It's not subjects within drugs within hospital. That's just not the notation. I like to think of it this way. When you have a design like that, the subjects can look up and see what levels they're in, but they can't see anything else over here and over here. So they don't know that. They just know, I'm in this hospital with this, or this drug, this hospital. I don't know what these guys over here are doing. So what, 5? Yeah, 5 participants in each group, 5 subjects. So that's n minus 1, so that's 4 times 2 times 3. And we test both hospitals and drugs within hospital using this error term, subjects within drugs by hospital. And if you threw this design in SPSS and specified the model, which you can do, you have to specify the model so much, you just specify the sources of variation. So you would have hospitals, drugs within hospitals, subjects by drugs by hospital, within drugs by hospital. It would do the correct. Is that helping you, Jared? You still have your question?
Oh, yeah.
Yeah.
Of course, like I thought you were going to explain everything else, but ask better.
Yeah, that's right. So yeah, this is something, and as I said, this is a real thing, and my friend here, Todd, who was my TA in my staff class actually when I was in grad school, he said, he told the people, this is how you analyze this. And they didn't, of course, understand anything. They just wanted to know if the drugs were different. The first thing he actually said was, can you just do all the drugs in all the hospitals? So can you collect more data? They said, no, we've spent all the money and there are no more burn survivors. And he said, oh, okay, that makes sense. You haven't, well, then, you haven't spent all the money, have you? Because I'm costing $250 an hour. So this is a case where this is not an ideal design. This is, in fact, the worst design in the world. It's almost, oh, it's not the worst. The very worst thing would be if we just had some empty ones, which is what we'll talk about on Tuesday. But this is pretty bad. We don't care about the hospital effect. It's uninteresting to us. Hospitals probably are different. There probably is an effect. That's not what we really care about. We care about drugs within hospital. But take a look at this. So if I find that the drugs are different, what I'm actually saying is within each hospital, drugs are different. So I didn't say the drugs are different. I said drugs within the hospitals are different. You then can look at the data, make some conclusions. There's other sort of post hoc tests you can do. But all this is telling you is that drugs within each hospital are different. 2 drugs within 3 of the hospitals are different. Sorry, within at least one of the 3 hospitals.
is it essentially just like the only situation in which you might use this is where you just can't get enough data to do a better design?
It's one of the places. The only other time I've used something like this, but I did it on purpose. And that's when I looked at, I can just pull this up for a sec. Yeah, I can just draw here. I had an experiment where I had two groups. We'll just call them group 1 and group 2. I don't want to get it too complicated. And then the two groups had various trials. Okay, they were run, there were groups of birds, and they were run every day. So we have trial 1, trial 2, trial 3, trial 4, trial 5. And we're going to call that, I called it block 1. It's not a randomized block design, it's just block 1. Trial 6, trial 7, trial 8, trial 9, trial 10. That's block 2. So something like this, and I was looking at learning between two groups. So actually, yeah, group 1 had, so these are two different, this is, we'll call this A1 and A2. So this is, let's call it A1 and A2. A1 was repeating stimuli, and A2 was unique stimuli each day. This is my master's thesis. And in this case, I wanted to see if I binned these trials, these 5 trials, into one block. So instead of having a learning curve that looked like this, I could draw something that looked like this, because it was averaged out. So in this case, trials are nested within block. It was just a way for me to do the analysis and see if there's a block effect, because I want to see if there's a block effect. Each trial, of course, each trial is going to be different. It's every single day. Yeah.
So just to make your data make sense when you put it on.
Yeah, it was just a way to, yeah, and in fact, frankly, most people don't do it like this. They just take the blocks and they ignore the trials. And when I was doing my analysis, I thought I should probably just do trials individually, because that sucks more variance out. And the more variance I can explain, the better. I mean, that's just always the way you should think of it. So yeah, in that case, I did it that way. And I think, yeah, that's, if you want to look up the paper, that's brought back Hierarchical Shuttleworth, 1992. We did it in 89, 88. So that's not the only time you do it. I mean, I've done it on purpose, but in that case, it's not that I care too much about the trial difference. In this case here, we actually care about the drugs in their hospitals. The idea that animals each day are different is not an exciting thing. Again, the fact that they would improve vastly over time, that's what I care about. Okay. By the way, those were learning curves, and when anybody says something has a steep learning curve, that actually means it's easy. Think about this for a second. If we're measuring learning, we're quantifying learning. On the y-axis, we have learning. On the x-axis, we have trials. If you learn from 0 to 100% in one trial, that's a very steep curve. That means it was easy. That's not a really steep learning curve. You mean it's easy? A very gradual learning curve actually means it's really hard. Just because the thing looks like it will be hard to climb, because you imagine climbing a graph. Sorry, this is something that bothers experimental psychologists. And somehow the words a steep learning curve have entered the general lexicon, meaning something's hard, but actually means it's easy. I'm sorry.
Next time I get looked at like a crazy person when I say there's a long learning curve,
Long would be okay, sure.
I believe you.
Yeah, please give me. You don't even have to give me mental credit. You can just say this guy said he knows what he's talking about. I literally met a friend that way, complaining that he said steep learning curve on a podcast. I emailed him. I said, "Yeah, you're wrong on this." That was in 2006. We're buddies. It's wild, isn't it? The world is weird. Let's do another example. N equals 3, again, I picked the number of subjects here. Unlike the drug hospital, which is a real study, this is just Oh, that was nice. Just like that. So here we have what? We got A, B, C's. We got 3 factors. Ooh. Let's put this over here. And now we have nesting and a within subject variable. Just to make it a little more complicated. Remember in Yates order and how to do this between subjects within, and the final piece of Yates order is you do the top of a hierarchy first and then the thing below. So that's what we had. Hospitals, drugs within hospitals. Okay. So what do we have here? What are our between subjects factors? Let's see. Well, not everybody gets every level of A, right? Because some subjects here get A1 and some get A2. What about B? B is also between. Yep. But B is nested within A, isn't it? See that? Because different levels of B occur with different levels of A. B1 and 2 are within A1, and B3 and 4 are within A2. C, however, is a within subject factor, isn't it? Because everybody gets every level of C. Everybody gets every level of C. Okay. So, between subjects within, our between subjects factors are A and B. We're going to have A listed first because it's the top of the hierarchy. And then we're going to say B within A, and then we're going to go from there. And that's what I have written here. Look. We got A, B within A. Let's not worry about what we're testing with what yet. And in fact, it's always just the thing below it with subjects. That doesn't change. Subjects are within A-B combinations. We can't interact any of these, so now let's C, and then we go C by A, C by B within A, C by S within AB, done. We had 3 subjects per group, 8 cells, so we have 8 times 3, 24 observations, so we have 23 degrees of freedom. Let's do the degrees of freedom and see if they add up. Well, we have 2 levels of A, so A minus 1 is 1. B within A has B minus 1. There are, within each level of A, there are 2 levels of B. So 2 minus 1 is 1 times 2. There's 2 levels of A. So that's going down to 2. N minus 1, so that was 3 minus 1 is 2, times 2 levels of A. Right? 2 times 2 is 4. Times 2 levels of B. There are 2 levels of B within each level of A. That's going to be 8. And then 1, 1, 2, 8. You add them up. 1 and 2 is 3, and 8 is 11, 12, 13, 14, 15, and 8 is 23. We did it right. And then, like I said, when you think about what to test with what, and you go to do the mean square, what mean square you divide by what of the mean square, that rule doesn't change. You just say we test mean square A by mean square for S within AB. Mean square for B within A by mean square for S within AB, etc. Okay? Questions on that one? You should be able to go the other way, which we just did on the quiz. So let's take a look at this. This one doesn't, and first thing you can see with this one is it actually doesn't have any nesting. But we go between subjects within. That immediately should tell you that B's a between and A's a within. How many levels of B do we have? That's right. How many levels of A do we have? 3. Now, here's the question. Are A and B crossed with each other? Well, in other words, all levels of A occur with all levels of B, and you can actually see that there's a term here called A by B, so yes. There's no nesting to worry about, so we can just pull that up. There's a little eraser here. Never tire of that joke. So let's just do this. Yeah, I erased there. I'm going to go over here and do it. That's great. So we got two levels. So we have three of B and three of A. So B1, 2, 3. And 1, 2, 3. Okay, subjects are within B. That means different subjects get different levels of B. So group 1, group 1, group 1, group 2, group 2. And then group 3, group 3, group 3. Almost done. Finally, how many subjects are there per group? Well, there's a couple ways to figure this out. We have 35 degrees of freedom. So we have big N equals 36. We have 9 cells. 9 times 4 is 36. N equals 4. You do that, there you go, 10 marks on the final exam. The finals were at 80. It's like twice the size of the last test. And there's going to be, I think there's 3 or 4 of these. Probably closer. Haven't made it all up yet. I changed a little bit every year, but not a lot, because I know it's a really good measuring instrument. Yeah. So practice these things. So remember, using Yates order, we can figure out any design and its error terms. So using this heuristic, this way of just, it's actually more of an algorithm when you think about it. You should be able to solve these things really pretty easily. And the nice thing is, once you've done it, and let's say you're doing it on the final exam, you have 2 hours to do the final exam, you'll be done. Get those questions done, do the other stuff, and come back to them and do it backwards. So let's say it's produced a design from the table like we just did there. If that's the case, just go backwards. Produce the table, try to get the design back. Or get the table, or whatever. Right? Got a little problem here. And it's a problem I'm just going to sort of leave hanging there because there's not a lot I can do about it. But are hospitals a fixed factor or a random factor? Yes. I think they're a random factor. They're kind of like subjects. Like the idea that different hospitals would be different shouldn't surprise us, and we wouldn't care, kind of like subjects. We also, while we didn't choose the hospitals randomly, it's just 3 hospitals that were able to be in the study. We want to generalize to every hospital. That sounds like a random factor. It sounds like it fits the bill of a random factor. The nice thing in that design, by the way, is if it's a random factor or a fixed factor, I think the error terms okay. But when these things get complicated, figuring out error terms gets complicated, basically. So when you start having fixed and random factors, other than the subject factor, it changes what you test with y, and things just get complicated. So I would avoid these designs like COVID-19. Like the plague we're literally going through right now. First thing up this slide, there wasn't a plague. Well, there were plagues. Not a global. Avoid these the way you avoid COVID-19. Wear a mask around these designs at all times. Seriously, I just don't. Except under the specific thing, like I said, when I used trials within blocks, my kid did that too on her master's thesis as well. I mean, she had learning curves, and yeah, just to look at blocks of bins of trials. Because I think she had like 3,000 trials in these different birds doing things. Because my kid also works on bird cognition because she's gone into the family business. Her work is so much cooler than anything I've ever done. Finding out how birds use the Earth's magnetic field to migrate is a lot cooler than how the chickadees find food basically. Just saying. I'm not saying my stuff wasn't cool, I'm saying her stuff's super cool. She's coming to visit tomorrow, and I was hoping that, it's too bad because my own behavior class is down to student presentations, because it would be, here's our guest lecturer, my daughter, take it away, honey. But no. Anyway, so she used it as well, the same thing though with the blocks, trials to block. But something like these last two designs of this lecture today, yeah, I wouldn't do. They're not good. Because think about this. When I find that drugs are in hospital, which is when this guy I know Todd, when he found this, he reported it back to them and he said, yeah, the drugs are different within each hospital. And they said, well, you mean the drugs are different? He goes, nah, not exactly. I mean, within at least one of the hospitals, two of the drugs are different. Okay, do you know which hospital? Well, not really. And technically, it's not only within a hospital, it's within it could be within two different hospitals, two drugs are different. And then he kept saying, could you collect more data? And they said, we're paying you $250 an hour for this? And he's like, I'm not gonna lie to you. So that's just the thing. Questions about these kind of designs?